In the beginning of this lesson, we'll try to revise what's remaining and took in the last lessons. So we talked about the condensate phases of matters, which are solids and liquids. So we explained what are the famous gases in the periodic table and their location in the right top place. The potential energy diagrams. What is the potential energy? What is the potential energy of a gas, of a liquid, of a solid? The gas has the highest potential energy in its particles. The liquid is lower and the solid is much lower. And we see the phase changes from one state, physical state to another. In these physical changes, there is changes in energy also of the particles. The potential energy increases, either decrease or increase. So energy is either released or absorbed. We saw the evaporation and the fusion. We saw also the condensation and the freezing, the sublimation and deposition. Some of them you have to move from a phase where you have high potential energy to a lower one. That's why the energy is decreased. This energy decrease in the particles means that energy is lost to the outside, which is an exothermic reaction. While if you had to increase the potential energy by moving from solid to gas, for example, you have to get some more energy, and you get this by absorption, by endothermic reaction. So we saw any reactions here in the potential energy diagrams where the arrow going up is endothermic, while which is arrow going down is exothermic. We explained how the gram of steam is causing more severe burns than the gram of water because of the difference in the potential energy. Then go back to the lessons again from 1 to 6 to get the detailed explanation. What's the meaning of a volatile liquid? This is evaporation only of the particles of the volatile liquid. The surface particles only are evaporated, changes from gas, liquid into gas, just by what? Just by being in the room temperature, so they are evaporated, but the inner particles does not evaporate in the room temperature. So if the liquid particles evaporated and form gas particles, and then you close this container, these liquid particles changed into gas particles will start to hit each other, collide with each other, and start bumping, forming a pressure. So this is a gas pressure. We call this pressure formed from this liquid the vapor pressure. This is caused by the pressure of the particles on the container from inside. When you increase the temperature, the pressure increases. Why? Because more liquid particles have changed into gas particles and caused more collisions with the container and caused higher vapor pressure. The more you increase the temperature, the more the vapor pressure is there, because this is a direct relationship. So they are directly proportional in increase. We learned what's meant by the molar heat of vaporization. This is the definition of how much heat is required to change 1 mole of substance from the liquid into gas. That's why it's called evaporation or vaporization at the same temperature. This is the general formula which represents the molar heat of vaporization. Here the X is changed from liquid into gas. And this is examples of some of the molar heat of vaporizations or condensation for some of the substances. This should be vaporization because you have changed it from liquid to gas. What is the vapor pressure? We have explained now what is the vapor pressure. The condensate state of matter. When talking about the substance has higher boiling point, expected to have higher molar heat of vaporization, we explain this by the forces of attraction between the particles. Again, please go back to the lessons to explain how this happens. As a summary, because there is stronger attraction forces, the particles doesn't want to lose the connection between each other and form a gas. That's why they are not easily evaporated. It needs a lot of heat to break the bonds between these particles and change into gas. That's why higher molar heat of vaporization and vice versa. The lower heat of vaporization means lower boiling point. At lower temperature, the substance can be vaporized because the attraction forces between them is weak. They can easily break down or break apart from each other. The relationship between the vapor pressure and temperature is proportional, but not directly proportional as explained. And also we explained what is the boiling point. This is the temperature at which the liquid starts to vaporize. But now, what is vaporized? It's the particles anywhere in the solution, not only in the surface. If it was only particles in the surface, this happens in the volatile liquids. But if you are boiling, it means it's not just evaporation from the surface, it's from inside or anywhere inside. The boiling point is the temperature at which vapor pressure is equal to the surrounding pressure. So two pressures are working on this substance, external pressure and vapor pressure. If the vapor pressure is equal to the external pressure or the surrounding pressure, then the boiling happens. We knew how the altitude difference makes difference in the boiling point because it makes difference in the atmospheric pressure. As you go up a mountain, the atmospheric pressure decreases. Since the atmospheric pressure is decreasing, then you can say that the particle vapor pressure is the same, but the surrounding pressure difference. Since the surrounding pressure decreases up the mountain and increases down the mountain, so this means that the boiling point also will be different. Why is that? Because here at the top, the vapor pressure is the same while the atmospheric pressure has decreased. This has to cause the boiling point to decrease. While if you go down, since the atmospheric pressure has increased and the vapor pressure is the same, this causes the boiling point also to increase. If you have two containers with liquids, this saying that it boils at 78.5 and this boils at 100 degrees. If the atmospheric pressure is 750 millimeter G, what is the vapor pressure? Since the boiling, they are already boiling, so this means that the atmospheric pressure is equal to the vapor pressure. So the vapor pressure is equal. Both of them. We said that at the boiling point, the vapor pressure equal to atmospheric pressure, and this is the same atmospheric pressure, so they are both having the vapor pressure. Another reason is that because we mentioned that the relationship between the temperature and vapor pressure, don't forget what we said. We said that if we have two liquids, and these two liquids, they are two different liquids, but the temperature is the same, we said the vapor pressure is the same. So the temperature is the same here for the two liquids. They are both at the same temperature. The boiling point is different, but the temperature now is the same. So the vapor pressure is the same. What is the normal boiling point? We said the boiling point is the temperature at which the vapor pressure is equal to the surrounding pressure. What if the surrounding pressure or atmospheric pressure is 760 millimeter Hg or 1 atmosphere? So it will be called the normal boiling point of the liquid. The molar heat of fusion, this time instead of vaporization, you are making fusion, which means you are changing from the solid into liquid. This is the energy required to change the substance, 1 mole of the substance, that's why it's called molar, from solid to liquid at the same temperature and constant pressure. Please note that the molar heat of fusion is less than the molar heat of vaporization. For example, the molar heat of fusion of water is 7 times less than the molar heat of vaporization. We explained why is that, because we said, as you can see here in the potential energy diagram, is a lot difference between the potential energy when there is liquid and gas. So the amount of heat that you need to change the solid into liquid is not big amount because you don't separate them from each other. They are just a little bit looser. So the solids are very close to each other. This is a little bit some difference or gap. But if you want to make a gas, you have to separate every one. There is no two molecules connected to each other. That's why you need to break all the types of bonds, not some bonds only like here. You have to break some bonds, but here you have to break all the bonds. To break all the bonds, you need too much amount of heat. That's why you have to have a very high fusion vaporization. That's why we said that the vaporization energy is here in the water is 7 times the fusion molar heat of fusion.